Everything we believed about reality once felt unshakable. Time seemed to flow the same for everyone. Space appeared fixed and absolute. Light looked like just another wave. But one idea shattered all of it. What if time could stretch? What if space could bend? What if the universe wasn't a rigid stage, but something alive, flexible, and far stranger than anyone imagined? Welcome to Mattermosaic, piecing together the universe, one discovery at a time. Today, we explore how Albert Einstein transformed our understanding of reality itself through the theory of relativity. At the end of the 19th century, physics looked almost complete. Newton's laws had guided our understanding of motion and gravity for more than 200 years. Maxwell's equations had unified electricity and magnetism into a single, elegant framework. Many scientists believed that only a few small gaps remained before the workings of the universe would be fully understood. The world felt predictable, stable, and governed by rules that applied everywhere and always. One of the central assumptions of this worldview was that time was absolute. No matter where you were or how fast you moved, a second was a second. Space, too, was believed to be fixed, a stage on which the events of the universe unfolded. Everything operated within this solid, universal framework. But beneath this apparent certainty, small cracks had begun to appear. Scientists were puzzled by the nature of light. Sound waves needed air, water waves needed water. So it seemed logical that light, too, needed a medium to travel through. Something they called the luminiferous ether. The ether was imagined as an invisible substance filling all of space. If Earth moved through it, scientists expected to detect tiny changes in the speed of light, depending on our direction of travel. In 1887, Albert Michelson and Edward Morley built an extraordinarily sensitive experiment to measure those changes. But the results stunned everyone. No matter the orientation, no matter Earth's motion, the speed of light remained exactly the same. It didn't slow down. It didn't speed up. It simply refused to behave like ordinary waves. Most scientists tried to rescue the idea of the ether, imagining strange distortions or hidden effects to explain the results. But a young patent clerk named Albert Einstein asked a different question. What if light doesn't change? What if we must? Einstein proposed a radical idea. The speed of light is constant for everyone, no matter how fast they move. If this is true, then our concepts of time and space cannot be fixed. They must adjust themselves to preserve that constant speed. In this universe, time can slow down depending on your motion. Distances can shrink. Events that seem simultaneous to one person can occur at different times for someone else. The universe, it turned out, was not rigid at all. It was flexible, responsive, and deeply intertwined with motion. These ideas formed the basis of special relativity, published in 1905. One of its most famous consequences was a completely new understanding of mass and energy, captured in the equation E psi mc2. This relationship revealed that mass could be converted into energy and energy into mass. It explained the immense power of stars, the mechanisms of radioactive decay, and the foundation of nuclear physics. But Einstein knew his work was incomplete. Special relativity described a universe without gravity. To extend the theory, Einstein had to rethink gravity from the ground up. Newton described gravity as a force. Objects pulled on each other across space. It worked incredibly well, predicting everything from falling apples to the orbits of planets. But Newton never explained what the force actually was. How did the sun pull on Earth across 93 million miles? What carried that influence? Einstein believed gravity wasn't a force at all. He imagined space and time as interconnected, forming a single fabric, spacetime. Mass and energy, he proposed, bend this fabric. Objects don't orbit because they're pulled. They orbit because they're following the curved paths created by massive bodies. Space tells matter how to move, and matter tells space how to curve. This idea became general relativity, published in 1915 after years of struggle and mathematical innovation. General relativity made astonishing predictions. Light should bend when passing near massive objects. Time should slow down in stronger gravitational fields. Massive stars at the end of their lives could collapse into singularities, forming black holes. Ripples in space-time, gravitational waves, should spread across the universe whenever massive objects accelerated violently. At first, these predictions sounded impossible to test, but in 1919, during a total solar eclipse, astronomers led by Arthur Eddington photographed starlight passing near the Sun. The star's positions appeared slightly shifted, not by much, but exactly as Einstein predicted. Overnight, Einstein became a global figure, and relativity became a cornerstone of modern physics. Over the next century, observation after observation confirmed Einstein's ideas. Mercury's orbit, which had puzzled astronomers for decades, matched perfectly once relativity was applied. Radio signals from massive objects were delayed exactly as predicted due to the warping of spacetime. Observations of binary pulsars showed energy loss consistent with gravitational waves. And then, in 2015, the first direct detection of gravitational waves arrived, a faint whisper from two colliding black holes more than 1 billion light-years away. Einstein had predicted them a century earlier, and now humanity could finally listen to the vibrations of space-time itself. Black holes, once seen as mathematical curiosities, became real astrophysical objects. They formed at the hearts of galaxies. They swallowed stars whole. They warped time so severely that an hour near their edge might equal years far away. Relativity allowed us to understand these extreme environments with clarity and precision. Relativity also affects everyday life in ways we seldom notice. GPS satellites orbit Earth, where gravity is weaker and time runs slightly faster. Their clocks must be corrected using both special and general relativity. Otherwise, your navigation system would drift by kilometers. Particle accelerators, like those at CERN, rely on relativistic equations to predict how particles behave near the speed of light. Even the energy produced by the Sun, the fusion reactions that make life possible, depends on the mass-energy relationship Einstein uncovered. Einstein's theories also reshaped our view of the universe. Instead of a static cosmos, relativity allowed for expansion. Einstein initially resisted this idea, adding a cosmological constant to force the universe to remain stable. But when Edwin Hubble discovered that galaxies were moving away from us, Einstein reportedly called his earlier assumption his greatest blunder. Yet the cosmological constant returned a century later to help explain dark energy, the mysterious force driving the accelerating expansion of the universe. Even Einstein's mistakes contained seeds of future discovery. Relativity teaches us that reality is far more fluid than our senses reveal. Time can stretch and shrink. Space can bend and twist. Gravity is not a pull, but a geometry. The cosmos is not a fixed arena, but a dynamic, evolving structure. The deeper we look, the stranger and more astonishing the universe becomes. Einstein once wrote that the most beautiful experience we can have is the mysterious. Relativity is a monument to curiosity, a reminder that questioning even the most obvious assumptions can unlock entirely new worlds. By imagining what others dismissed, Einstein revealed a universe where space and time are alive, where mass is energy, and where the rules of reality shift depending on where you stand and how you move. As we continue to explore the universe, from gravitational waves to the edges of black holes, relativity remains our guide. It doesn't give final answers. Instead, it opens doors, leading us deeper into the fabric of existence. Every discovery raises new questions. Every mystery reveals a larger mystery behind it. This is Mattermosaic, piecing together the universe, one discovery at a time. If this video sparked your curiosity, leave a like, share it with someone who loves science, and tell us what you'd like to explore next. Subscribe for more weekly journeys through the fabric of reality.